So, I will continue this velocity of the electron in a band. So, it changes like this, and if you just you see, this is the now definition of velocity. Now, if you take the if you just consider the free electron not in a band. So, this what is the so we have to know the energy of this electron, free electron. So, energy of this free electron as a function of k, if you know, then you can find out the velocity. So, E equal to h cross square k square by 2n, right. So, d by dk equal to h cross square 2h cross square k by 2n, right. So, it is so your velocity v, so velocity v equal to 1 by h cross d by dk, right. So, equal to, so d by dk from here what I got. So, 2k 2h cross square k by 2m and 1 h cross is here. So, these two going, this h cross is going. So, I am getting v equal to k by m, right. V equal to k by m. So, here I did mistake. So, here basically h cross square is there. Okay. So, 1 h cross is gone. So, 1 h cross will be there. So, h cross k by m, right. For free electron, what is h cross k? That is p, momentum p. So, p by m. So, this just this free electron, right. So, p is mv, p is nothing but mv divided by m, it is a v, this is a v, right. So, this is a general definition of velocity of a electron, whether it is in lattice, whether it is in a band, or it is free electron. So, whatever, if you know the EK relation, you can find out the velocity. Okay. Another aspect of here what we have seen. So, v equal to h cross k by m, right. So, v is basically is proportional to, linearly proportional to k, right. So, it is just linear function. So, if I draw here, so for free electron what was the EK curve? It was just parabolic curve, right. CK, it is EK, it is parabolic curve. So, now corresponding velocity from here, if you draw, you can see this velocity here, this it just slope is changing continuously. There is no inflection point, it is changing. So, it is changing. Right. So, linearly it is changing, that is what here it is linearly changing. So, it is, you see, quite different, it is quite different for free. In case of free electron, just velocity is linearly changing with k, this axis is velocity, but here when electron is not free, it is in a band, okay, then its variation is quite different. Okay. So, it is important to notice that the velocity it depends on this relation E k relation for that electron. That electron in which situation it is, in which environment it is. So, that will decide, that environment will decide that E k relation, and corresponding velocity also follow that relation. So, another parameter is very important, that is effective mass, that is effective mass of a electron, effective mass of electron of an electron when it is in band. Okay. When it is in band. Okay. So, effective mass of electron, here also we will find out the definition of this effective mass. You know, acceleration, if you a electron is there, if you just apply electric field, so it will get force and it will be accelerated. So, when acceleration is basically change of velocity with time, right. So, when it is in lattice, so or it is just for general, so this velocity is this. So, I can write 1 by h cross d by dt, and that is d by dk, right. So, here I can write d2 e dk square, okay, then dk by dt. So, this with respect to dk. So, you will get this. Okay. So, acceleration is 1 by h cross d2 e by dk square dk dt. Okay. So, this when E k relation is known, we know, then we can find out d2 e by dk square. Okay. But what is this dk by dt? What is dk by dt? Okay. That we have to find out. So, if we apply the just electric field for a short time dt, that electron, initially that electron velocity is v. Okay. Now, we have applied electric field E. So, it will feel force of how much? It will feel force of how much? F equal to E, that electric field, right. Now, that electron will gain energy that will be equal to the work done by the external electric field on that electron, right. So, work done is basically that will be energy E equal to force into, due to that force, what is the distance is traversed. So, your force is this, and now its velocity is v, and electric field was applied for short time dt. So, it will travel distance v dt. So, force into that this distance that is v dt, okay, for short time it is applied. So, that will be the distance, and this will be the energy. So, this also small energy. So, dE equal to this, right. So, when we apply electric field on electron moving with velocity v for short time dt, so what will be the change of its energy? What energy it will gain? So, d energy it will gain. So, that is right. So, it is not, I think, time. So, you should write this. So, from here one can find out this that dk by dt, because this E is what is this E? Energy E is h cross omega, E is h cross omega. I think this yes, so this V, I think here I have to here. So, V dt, so V is by definition it is this. So, I can replace V by 1 by h cross square h cross dE by dk, right. So, what we are getting? So, dE equal to this dE. So, basically dt by dk. So, just if you take this side dk by dt, right. So, del E by del E is 1. So, dk by you will get dk by dt equal to E electric field 1 by h cross dk by dt 1 by h cross, right. Is it correct? Yes, I think so. So, dk by dt equal to this, so by h cross, right. So, this from here when we are getting this, so now this acceleration for a that we have seen, acceleration that we have seen, that is in terms of this, here we have written, now we have to find out dk dt. So, we got this dk dt. So, now I can replace this dk dt, now I can replace this dk dt by this term epsilon E electric field divided by h cross, right. So, we are getting basically acceleration, we are getting A equal to E this now 1 by h cross square 2 E by dt square dk square. Okay. So, for any particle, it can be electron, free electron. So, what is the force? F equal to, or we can write ma, right. That is the Newton's second law, ma, and in this case this force is, if we apply electric field on an electron, so it will field force how much? E epsilon for any charged particle, free particle. Okay. So, a charged particle of mass m, okay, if we apply this force, so then its acceleration will be A equal to this by m, right. Now, if I compare this two, then I can write this 1 by m equal to 1 by h cross square d2 E by dk square, right. So, whatever the, this mass, this mass generally we called effective mass, So, here effective mass, what I got, m star effective mass we defined by this. So, h cross square by d2 E by dk square, Okay. So, these are again general definition of mass, okay, whether electron is free or it is in lattice, just check it. So, you know that free electron, for free electron I have to know EK relation. So, that was H cross square k square by 2m, right. So, what will be d2E by dk square? So, dE by dk, it will be 2 H cross square into k by 2m, again differentiate, right. So, this k will go, 2 will go. So, H cross square by right. Now, if you put here m star equal to H cross square by this, that means by this H cross square by m. So, multiply it up, so equal to m, you see. So, for free electron, whatever this mass, effective mass, it is the same as its original mass. Okay. So, it is very interesting that it is long time it is known to us that mass of electron is well known and it is constant, right. It has some definite value, particular value, but when that electron is in a band, then its mass, how it change. So, interestingly you can see that this is the definition of mass, and d2E by dk square, what it is for this curve, d2E by dk square, it is nothing but the curvature of this curve. What is curvature? This its curvature, right. Okay. This curvature radius r. So, generally curvature is inversely proportional to this radius. This radius is higher, curvature is smaller. Radius is smaller, curvature is higher. Radius is higher, curvature is smaller. Okay. So, here in this curve there is two curvature, one is this, another is this, and this m represented by this. These are constant, forget. Okay. So, this curvature, so here if I draw, whether I can, let us see, yes, let us see. So, let me draw a slightly smaller size, this one, slightly smaller size, then I can so just I will draw like this, okay. This is just for space, I need space, so that is why. So, this is the inflection point, under this inflection point, okay. So, for mass, if I draw, this is k axis, these are k axis, right, and mass I am changing this way. This is the mass, effective mass, this is the effective, this is the velocity, right, this is the energy, and in this case what will happen? This star, okay. So, this is the curvature, right. So, here basically, and you will get this type of curve, it has to be symmetric, this type of curve, and at inflation it is just discontinue, and then this is this curvature and this the another curvature. So, just opposite to that. So, and you will get you will get this side, you will get, okay. So, it is, you can think, okay, from here you will see this type of change of effective mass you will see. What you will see? So, it is here it is positive, mass is positive, okay. See, it is at the edge of this, at the edge of this bilirubin, at the edge of the bilirubin or top level energy levels of band. So, this mass is negative, this mass is negative, right, but in middle of the band, in middle of the band this mass is positive, at the edge it is negative. So, before inflation, inflection point is a positive and after inflection point is a negative. So, this inflection point is the turning point of the curvature, you know. So, this is very important. So, before this inflection point and after inflection point, these things are, these change are different in case of velocity, in case of mass also. So, here negative mass. So, when electron in a band, so its mass can be negative. When that electron is in a, this is the band, this is the band, energy levels are there. When electrons are on the top of the energy band, so its mass can be the negative, right, and its velocity, when it is here, is velocity decrease, you know. So, when you are applying electric field, and because of that this electron are moving, right. So, when, so in this region here it is velocity 0, then it is increasing when it is reaching the some energy level, some places, and then it is, its velocity is decreased. So, why velocity decreased suddenly? So, that means you can think two ways. One is, so this electron are moving influence of external electric field, right. So, it is moving, its velocity will increase, and then there is acceleration, right. Now, suddenly after this point its velocity is decreasing. So, its velocity is decreasing means some deacceleration is working on it. If it is accelerated, its velocity will increase, then it is decreasing. Now, there is a deacceleration, there is a force on opposite side, okay, on that electron. So, you can consider that why suddenly this force is on opposite side. So, if you think that when electron are moving in this in top band, okay, then if we think that electron's charge becoming positive, electron charge is negative, now we can think that electron charge becoming positive. When electron charge becoming positive, then due to that electric field, it will feel force in opposite direction, right. Whatever the force it was enjoying because of its negative energy, negative charge. So, the direction of the force, now if it becomes suddenly become positive charge, then it will feel the opposite force. So, its velocity will decrease, right. So, this may be one case, that way we can explain this velocity decreasing and becoming 0 when it is reaching at the top, from here to top. Okay. So, this is one case. Second case, so this positive charge of electron becoming, having the positive charge, becoming positive charge. Is it possible? Yes, it is possible. So, that is called basically hole. So, that is called basically hole. Hole is having same electric charge whatever electron have, but it is positive charge. Okay. So, these are giving us impression or hints about the existence of hole, right, in solid. Similarly, other way one can think. So, when it is in upper band, right, upper band, so its mass is negative. So, you can think that electron is moving under a electric field. So, its negative charge, So, then it is moving with some force in one direction. Now, when suddenly its mass is whatever this mass was there. Now, when it is moving on the top of the band, then it's from positive mass to it is going towards negative mass, right. So, then also acceleration can be opposite side, because m that acceleration is. So, it can feel, because this force is m a, right, acceleration and this mass. So, this now if mass becomes suddenly negative, then force will act now minus m a kind of things. So, mass this force will act on this electron in opposite direction due to the negative mass. Okay. So, electron have basically negative charge, electron have basically positive mass, right, positive mass. So, but in upper band, we are getting that electron whatever we are charged, that is as if it is positive charge, okay. And yes, so when electron are here, so it's as if this electron mass is negative, right. Electron is here with negative charge, so is negative charge, so its mass is negative, right, mass is negative. Okay. So, electron here it has negative charge and negative mass here. So, now absence of this electron, we can think that vacancy, absence of this electron having negative charge and negative mass, absence of this, we can think this one is positive charge and positive mass. So, this one is nothing but the hole. Okay. Absence of electron is nothing but that act as a hole, that is positive charge and positive mass. Okay. So, electron here is negative charge and it become the negative mass. Now, absent of such from this top of the band, generally hole we find at the top of the band. So, absent of that electron having negative charge and negative mass, so that is equivalent to a hole which will have positive charge and positive mass. Okay. So, these are very interesting. So, this from conic penny model. So, lot of mathematics determinant you have to do, but whatever the condition we got, this set of expression, from there we extract a very rich physics and very interesting also. One can explain the band, explain the electrical property of different material, whether it is insulator, it is semiconductor, it is metal, okay. And also it can give the concept of, it can give hints of the concept of hole, right. And this effective mass, this Ma equal to this one. So, yeah. So, from here this basically Ek relation, you know, I have shown this for electron, free electron, that is m star equal to m. So, this is the general definition. So, for free electron, whatever the energy expression E equal to h cross square k square by 2m CPU, replace this m by m star effective mass. So, this equation is valid for others also. Okay. It is not only valid for free electron, it is valid for other electrons also, whether electrons in band or for other. If you know the Ek relation of that electron, so you can find out the energy. Okay. So, these are very interesting. I think there are many things we discuss about the energy, about the band, and this band contains the how many orbitals, how electrons are distributed among them, how when it will show the show as a metal behavior or semiconducting behavior or insulating behavior, right. And velocity, mass, they are quite different from the free electron. Okay. So, now I will stop here. So, basically band structure, using the band structure, so you can classify different material. So, now in next I will teach you about this semiconductor crystal, semiconductor physics. Okay. So, how one can define semiconductor and what are the types of semiconductor. So, that I will discuss in next class. So, thank you for your attention.